right, well, thank you, Carl, and it's great to be back at DARPA ERI. I was in Detroit in 2019, which was the last in-person ERI, and it's phenomenal to see not only the great content, but the great networking of our industry just absolutely needs this, and so hopefully you've been leveraging that. Well, look, I'm very excited about the topic that I'm going to bring this to a close with here today. After, as I said, just really exciting content, and the content was all about innovation, and that's really the topic of the next few minutes. I want to give you a little context of my view, our view at AMD, in terms of the kind of innovation we need to meet what is, just such an exploding demand for compute capacity and capability in AI and HPC. You know, DARPA has been really fostering accelerated computing for so many years, and we're proud at AMD to be able to have partnered on not only historic DARPA programs, but our ongoing collaborations. And what we're really committed to at AMD is a very strong public-private partnership, and that's what DARPA MTO has really exemplified. And let's look at a few examples of where we're going to need innovation and partnership to meet the needs of our industry. I'll start with what you might say is certainly obvious to all of us at this point, and that is this incredible expanding application space of AI. It's not a buzzword, it's real. And what I think is clear to all of us is the kind of compute capabilities that used to be developed just for supercomputers, and supercomputers would be in just a handful of really country-run installations because that's the kind of investment that is needed. Now that's expanded. You saw that expand across dozens of HPC facilities in the last 10 years. But what's happened now with the type of computing needed to develop large language models and really amazingly complex generative AI capabilities is that type of supercomputing capability is much more widely needed, and it's a matter of national interest to have that capability. But with it, what you're seeing is it being deployed to address societal challenges across our work, our home life processes, the very creative processes that we deploy every day, and it's really speeding progress. It's an incredible augmentation. We have such a mass accumulation of data. Of course, it's the years and years of human-generated data, and now this machine-generated data that we have from these embedded devices all around us. What these AI capabilities are allowing us to do is to put that data to work, and if we do it right, and we have the right governance, and we have the right policies in place, it will provide incredible societal good. And it's amazing the pace that we've been on. It was just 10 years ago that we saw those advances with deep neural nets, and we were starting to get accuracy with natural language recognition and image recognition. And here we are a decade later. And I can tell you just from my experience, as we've applied AI techniques at our chip processing development in AMD, everywhere that we apply it, we're seeing tremendous benefit. It's right in the very ways in which we place and route our chip designs, the way we verify it, the way we code the software enablement and our business processes. And it's so personally fulfilling when you've had 4+ decades like I have in this industry to see the very chip designs we work on being able to power such a demonstrable, immediate and tangible improvements to our productivity. So with that, let's look at what's coming ahead. Well, folks, again, I'm not telling you anything you don't know. It ain't slowing down, right? We're seeing such a tremendous growth of compute capacity, and the reason is very simple. All of the old demands that you had on computing, that you ran your lives on before these new AI capabilities came about, they didn't really go away. What you're adding on top of it is predictive and generative AI capabilities. And so it's creating basically a double exponential It's an and, not an or function of computing capability. And what we've seen is, just a tremendous need for more innovation. We've already been investing in CPU and GPU computing. We've been, heavily invested and helped lead the way at AMD with heterogeneous compute approaches. But what we're now seeing is how you put not only CPU, GPUs, but other fixed function accelerators together, and more importantly, how you optimize at a system level is the key to be able to propel us to the future. We all know it. Moore's law has slowed down. We have to have this type of system-level innovation to be able to meet these insatiable demands for more computing. So let's talk about how we think about that innovation. Let me give you just several factors to think about as we put it together. The first is thinking about the power of community in solving solutions, the importance of an open ecosystem. AMD has always been a staunch supporter of open ecosystems. In fact, our software stack is predominantly open, whether it be our LLVM compilers or across the AI stack, our ROCm enablement that we've opened up. But what this does is it brings in the community to co-optimize and to expand the capabilities. Likewise, hardware, it needs community. We're a member of the Key Standards Committee and an important consortia like Open Compute Project, Calyptra, and Chip Security, a CXL to be able to expand your server compute systems, UCIe to drive chiplet connectivity, and most recently, the Ultra Ethernet Consortium, which will allow much more competition in AI-ready network configurations. So both with software and hardware, that value of the community is absolutely critical to be able to innovate on the pace we need to grow and meet the computing requirements of the industry. The other thing that I want to highlight is modularity. It's another really important factor in meeting those needs that often goes unlooked. And we've found that the ability to think about that modularity in every aspect of the design not only speeds that innovation process because you can have more flexibility in putting that solution together, but you can also drive resource reuse, whether it be IP, chiplet resource, software elements. You can drive more resource, so it's much more efficient as well. And what we've done at AMD to be able to speed those type of tailored solutions is we architected for it. We architected the Infinity architecture, the Infinity fabric, which is our connectivity. So it starts with the IPs we put together. You can look at the latest Ryzen, that's our combined CPU and GPU chip that we use for PCs and embedded. And our latest Ryzen 7040 included not only that CPU and GPU and other accelerators, but a new AI engine that really speeds AI inferencing. And you're going to see all kinds of new features that can start to take advantage when you have that number of TOPS, that number of AI inference acceleration capability in such a small and energy efficient chip. And likewise, I'll talk a little bit later about our new data center GPU chip, and you'll see firsthand some of that flexibility of chiplets and how it allows you flexibility to move quickly to meet tailored computing demands. And then, of course, how you put the systems together, leveraging modularity to attend to the workload at hand, and software, being able to take advantage of a stack that, again, is tailored to the workload at hand. So going on, as you look at sort of that implementation of innovation efficiency, we need also to be able to pack these solutions more efficiently. And chiplets, as well as the packaging technologies associated with it, have been going through an incredible innovation phase and will be even more important. In fact, it's certainly one of the key focus areas of CHIPS Act as investment to accelerate our packaging capabilities and innovation. And I can tell you that because we focus on high performance computing at AMD, we have been focused in this area And you can go back to how we've stacked devices, starting with HBM stacked on a 2.5D silicon interposer back in 2015. Xilinx has done the same thing, leveraging 2.5D to be able to drive leadership gate capabilities in adaptive and FPGA devices, and then growing that as we mix nodes. So you can look at the AMD EPYC server or high-performance desktop products that we have, where we'll have a CPU compute chip on the most advanced die, and then connected to an I/O and memory device on an N-1 node. So again, really effective use of packaging to get more density, more efficient computing, but also more economic and more flexible. And then you can look at both elevated fan-out bridge, as we had in the Instinct 250, and which leveraged both 3D stacking and horizontal 2.5D, and in 3D stacking for the CPU, the AMD 3D V-Cache, which brings memory, additional cache memory directly on top of the CPU, providing you, for instance, in EDA workloads, up to a 60% performance advantage by bringing that memory so close in to the computing device. And then again, I'll show you in just a minute, I want to show you an example in MI300, our upcoming data center GPU device, how we've leveraged chiplet packaging and that flexibility. But before I do that, let me just sort of lay the stage of just emphasizing how important these design approaches are, and really challenging each of you, as you've kind of covered in the various talks today, about thinking about that innovation in multiple faceted ways. Thinking about it from the chip delivery itself, how you're putting those chip solutions together, how you're delivering power, how you're bringing a system solution together, including how you're integrating the software and hardware. This is an area that we have to tackle as an industry to be able to further enable design innovations. And what I call it here is holistic design, because the only way that we're going to stay on that torrid pace that we've enjoyed for decades in this industry, when we got that historic lift of Moore's Law on the semiconductor device itself, is we're going to have to innovate more holistically from starting actually on the end application, understanding the workloads, understanding where the key bottlenecks are, and working ourselves back down through this software stack, through how we're implementing the compute elements together, down to how we're implementing and optimizing the devices, and all the way down to the silicon and process level. I can tell you at AMD, we're finding that we need to work across this full circle of innovation, including even the manufacturers of the equipment in the fab are needing to understand how these devices are coming together. So it's not a foreign approach to any of us, but it's never been as imperative that we double down on our game in terms of how we collaborate across these innovation stacks. So I said I would come back to our next generation data center GPU. I couldn't be more excited about what we have coming together in MI300. And I'll tell you, it's a perfect example of that call out I had of holistic design. Because the MI300 data center GPU achieves both leadership HPC and AI performance. So there's two versions of this design. It leverages 5 nanometer technology. It has a base die from logic function, but on top of that, it's 3D stacked with a combination of CPU and GPU chips. It has a combination of up to 153 billion transistors. That comes with a few challenges that you have to solve along the way. But it is indeed integrated from a hardware and software to be able to facilitate and to lead in AI applications. The HBM stack brings, along with the GPU computing capability, brings absolute leadership AI inferencing capability. And in the HPC version, you're seeing it being stood up today in the world's largest supercomputer, which will be at the Lawrence Livermore Lab. And so when you look at that chiplet capability, being able to pivot from that HPC design that started with the CPU chiplets along with the GPU chiplets to a GPU-only design, which is ideal for the large language model AI processing that you need in the largest data centers. So tremendous flexibility, and you don't need any more evidence than our computers, than the announcement made today by our competitor in data center GPU that this industry needs competition. And that's exactly what we're doing with AMD with our Instinct MI300. We're bringing competition to GPU compute in the data center. We're very excited this will be starting shipping at the end of the year. Also, I mentioned the criticality of software, and you see this will be supported, for instance, by thousands of models that come out with Hugging Face will all be validated on the MI300. PyTorch 2.0 has certified with AMD, as well as a full suite of compiler and support tools. So a very exciting time in the industry as we're starting to see more competition in such an incredibly demanding high-performance computing. Excuse me. So while we've made a lot of progress, certainly more to go. I'll give you just several examples here. This is system energy associated with memory access power is increasing dramatically. The per bit energy is actually improving in every generation, but the overall memory capacity and bandwidth demands are actually outstripping the design improvements and process improvements that we're being able to make in each generation. And so what you can see is this is simply going to continue going forward. So thinking about memory and bringing memory more efficiently to the compute elements is fundamental. So we're going to need an even tighter integration of compute and memory going forward. What you think about, look at the left side, you see a typical DDR5 module. Look, it's the workhorse of our server industry today, but it's also a high consumer of energy if you look at any of these systems. And so what have we done? I mentioned earlier when I talked about packaging with stacked HBM and bringing that with 2.5D packaging. That increases the energy efficiency by 4 to 5x, so it's certainly an important improvement. But what if you stack that memory vertically right over the computing elements itself? Well, that's an order of magnitude of more efficient computing in terms of its efficiency, so it lowers that power by providing that adjacency, and it also, of course, gives you substantially more bandwidth. We're doing that today with SRAM stacked, as I mentioned, with our AMD 3D V-Cache, and I'd ask you to look ahead and challenge you. Can we stack DRAM going forward and bring even higher density of memories to get that order of magnitude efficiency? Well, we can if we continue to focus on these packaging improvements, on techniques such as hybrid bonding, as well as how we think about even other ways to interconnect these solutions. I'll pivot into optical interconnect, where co-packaged optics has a tremendous opportunity to not only also lower us to less than a picojoule per bit of that energy to connect, but also from a standpoint of being able to give us distance to disaggregate our solutions and be able to give our computing solutions more flexibility of integration. So this is a very exciting area, and we've been very proud with DARPA to have participated in the PIPES program, which demonstrated exactly this co-packaged optics capability on Ethernet networking. So again, what happens when we innovate and we drive more and more compute packing and driving the efficiency in that way? We're going to have to solve challenges of heat and power density. And it's going to take new innovations in terms of our thermal materials, how we go about cooling, how we design for those thermal constraints from the get-go. So we're going to need our EDA vendors to embrace 3D integration and actually end-to-end analysis through the package assembly, through the card design. That's what holistic design is. That's what it requires. Likewise, the same in terms of power efficiency and regulation. we're going to, for these HPC and AI applications, not only need to improve the per core regulation, which we're doing today, but drive more efficient integration, lowering the inductive power loss in our packaging. And it's this optimized power delivery network that we need for the complex multi-chiplet integrations that we have and need for AI computing. So look, I want to conclude by just telling you that I think you have to agree, it's an incredibly exciting time. We need to embrace the challenges that these high-performance systems offer to us. It's going to be cross-disciplinary. It's going to drive all of us to operate in a holistic design mode. And AMD is ready. We're ready to deliver leadership solutions, but do it by partnering with our customers, partnering with the industry, and partnering with the government on public-private partnership to deliver leadership, AI, and high-performance solutions. Thank you.